So we'll talk through it.
Okay, I got you.
So we'll go ahead and talk through this. I want to point out some things. I'm already getting people being like, before. Let's chill. Awesome. You're calling out but for. Why are you calling out but for? Why is but for wrong? It's multiplication division. We have to go based off the fewest Sig Figs. Was that 5, 3, 6? 3 is our answer. 4, 5, 3. We look at the first digit afterwards. That digit is larger than 5, so I need to add 1. So my number needs to become 454. Not for real. I'm just checking. I'm off by 1,000. Okay. I need that last 0. What is that last 0? That's a placeholder to make sure the other numbers fall correctly. Okay, makes sense? So we still have just 3 Sig Figs. You need the 0 as a placeholder. Okay, so I'm kind of surprised by the overwhelming, like, Mike, you're an idiot. That's awesome. Okay, because yeah, that 0 is very commonly dropped off. We do need to keep it there. Okay, the rest of them, I think I did the last one right. We get 3 Sig Figs, 454. Okay, so all those numbers should be good. I do want to point out a couple things. Number of Sig Figs in 3. What do we got? 5, 3, 6. Our answer has how many Sig Figs? 5. Wait, am I allowed to do that?
No.
Yes. Why?
It's addition.
It's addition, subtraction. Okay? When we add numbers, we have the ability to actually increase the amount of significant digits. Okay? That in and of itself isn't the big issue. The big issue actually hits us in 5. What happened in 5? We started with 4, or that's a lot of numbers.
6.
There's 7? 6. And we end with 1 significant digit. Since that is the only significant digit, that digit by definition is a guess. Which means by running the calculation with those measurements, I have lost all meaning in my calculation. So if we're ever in a situation where we need to calculate something by difference, by doing a subtraction, we try to make sure that that difference is as large as humanly possible so that we don't lose significant digits. Okay? The smaller that difference, the more likely that we introduce error into our measurements. Okay? So subtraction's a really dangerous one when we're going through and doing measurements. Okay? Addition isn't dangerous, it's actually cool because we could get more information by the end of it. There were a couple hands. Was that you, Nadia?
So for multiplication and division, it matters how many Sig Figs you have?
It always matters your Sig Figs. The number of Sig Figs is important in multiplication and division. Addition and subtraction has to do with the place of precision. Okay? So Sig Figs is always important, but the actual counting of Sig Figs becomes super important because that's how we define our answer in multiplication division.
So, again with number 5, like how would we figure a way to make the difference bigger even though it's only...
So typically what we would do there, in this case that was measuring a liters, so a volume. What I would do is, what I'm probably trying to do is measure a volume to get to a certain point of a reaction. Well, that reaction is dependent on certain things, like how much chemical is actually there. So what I could do is make a solution where I dilute the chemical. If there's less chemical there, it's going to take a larger volume for it to transfer across.
Okay.
We're officially pushing at that point now into Unit 3. Okay. So if you didn't get that, don't stress. At least JC's got that. We'll see that in a little bit. Ethan first, I think.
Okay, so well, number 5, it was like I got like 2 or 0.0252. You know, that was like all the way out.
So yeah, your calculator 0.0252.
Yeah. It's like
Okay.
three significant figures.
You can only report, because this is addition subtraction, you can only report to the least precise place. The least precise place is the hundredths place, so I can only report to that 2. I take a look at that first not significant digit. It is 5 or larger. I need to add 1. That's how I get to the 0.03.
On number 3, there's supposed to be a 1 after the 4.
No, there's not.
It's there when you calculate it, but it's dropped off.
Addition, subtraction, least precise place. The least precise place here is the hundredths. 0 hundredths. There may be another number out there. Should I be reporting that 1? No, because that 1 is not a significant digit.
So you have to do like the least amount of Sig Figs?
For addition, subtraction, it's the least precise place. Okay?
So then it's 1.
And I know you're about to write something down. You might get out your phone and take a picture in a second. What was your question? Did you have a question? No. Okay. And why might I say take out your calculator? It might be useful to have it all on one slide. Or not your calculator. Your phone. Get a picture. There you go. All the rules. You get all your significant digit rules, your addition, subtraction, multiplication, division, and rounding down on one slide. Okay? I fully told you to take pictures. That's cool. You do also have these slides, just so you know. So, this one I posted very late. I think I posted it Tuesday morning. Okay, but it should be up there. If you can't find it, talk to me, and I'll direct you to it. Okay, so qualitative, quantitative, we already talked about, but what we're doing is jumping back into chapter 3 with physical and chemical properties. Okay. I have a hard time with physical and chemical properties, so I fully expect you to also have a hard time with it. Okay. Primary reason is chemical properties. What is a chemical property? It's how it interacts, and it's not even how it interacts, it's how it reacts, as in making or breaking bonds with other compounds. Okay. So you hear people, oh, well, that's flammability. You mean how it reacts with oxygen? Yeah. Why don't you just say it's how it reacts with oxygen? Okay, so there's chemical reactions that we call as properties, which are weird to label as properties. It's really a chemical reaction. So all of our chemical properties are how does it react with another species. Okay? The physical properties, we keep that compound intact. We don't make or break bonds, but we can change phases. We can pass electricity through it. We can pass heat through it, those kind of things. So whatever you do to it that doesn't change its physical identity or chemical identity. Chemical and physical changes, ultimately the same thing, yada, yada, yada. This is the cool part. Evidence for chemical reactions. This is a summary slide. You've already seen this because you watched the Play Pause It video.
Yes.
Okay? So that should all be familiar, right? Questions about any of it? Nope. Okay. There's pictures. What do we see here? This is a color change. We started with 2 clear solutions and we got yellow. What else is it? A little bit harder to tell. That's a solid forming. That's a yellow precipitate. So we got a color change and a phase change. Both of those suggest a chemical property. What's happening in that one?
Sparks are combined.
We're seeing sparks. What are sparks? Light. What is light? Energy. And energy change is observed. Okay? So this is a fun one to look at. Chemical or physical? So let's work through this one. Melting ice, what do you think? Chemical or physical? Okay, that is purely physical. Dissolving sugar. Okay, hold on, so we'll wait. Burning wood. Definitely chemical. Dissolving salt. What does sugar look like? A white solid, right? What does salt look like? A white solid. We're asking about dissolving in water. What's the difference when we add sugar to water versus salt to water? We don't see any difference, right? Okay. This is where it becomes challenging. When we dissolve sugar into water, we don't break any of the chemical bonds in sugar. So the dissolving of sugar is physical. When we dissolve salt, what happens? We break the bond. The bond, because the bond in salt is ionic. That ionic bond breaks when it hits water. Because we've now broken a bond, that is chemical. As we discussed in the lab, we could reference chemical and physical versus reversible and irreversible. Chemical changes are irreversible. It's kind of way over the top, but let's go with it. Physical changes are reversible. Can I get the salt back once I've dissolved it in water?
Yes.
By doing what? Boiling off the water. Isn't that reversible? So dissolving salt, chemical or physical? Okay. You notice that I've picked red and purple. I'm going to argue that dissolving salt is actually green chemical. Why a different color? What we're looking at between chemical and physical is a spectrum of differences. Okay? When we talk about black and white, is it really black and white? No, there's a whole bunch of gray area as we transition in between. Chemical and physical changes are the same thing. There are some changes that are very clearly chemical. There are some changes that are very clearly physical. There are also some changes that straddle kind of in between both of those categories and make it very difficult to interpret. Okay? Unless you have more advanced knowledge of what's going on. You're starting to get more advanced knowledge. Knowing that dissolving salt is chemical, I would argue, is not part of your advanced knowledge. Food dye with white cake frosting. That's reversible? It's like, that's totally not reversible. Believe it or not, it is. It is very difficult to reverse. Okay? But it is absolutely reversible. How do you reverse it? When you got the red dye into the frosting, how did you do it? You mixed, right? If you go back the exact same direction, you actually reverse it. Okay? There's a video for this that I can actually show because we can do it with glycerin. Okay? We can take glycerin and food dye and you can actually watch the reversing process. Why is it so difficult? How consistent are humans in their mixing ability and the ability to hit the exact same location in space? Not very good. Okay, but if we use a machine to run through that motion, we could actually very carefully mix it all together and then also unmix it. Okay, which is pretty fascinating. The last one, I know I'm out of time, but I think this one's kind of cool. What do you think? Okay, you might need some context. We took this yellow crystal, we shined light on it. When we shined light on it, it became purple. We remove the light, what happens? Goes back to yellow. It is exactly like those glasses. In fact, these compounds are typically found in those glasses.
I have perfect vision, so
How would we know? We would have to actually dig into this to study what's happening at the chemical level. When we get down to the chemical level, what's happening? The ultraviolet light that we shine on it causes the bonds to rearrange and form a different structure. That different structure interacts with light differently, and we get a different color. That molecule, when I remove that ultraviolet light, that energy source, will thermally, so just the ambient temperature in the air, will revert back to its original state by breaking chemical bonds. When it comes to rules about adding or subtracting with any chemical or physical, it's usually a bad idea. Okay? So don't use it as a rule. You can say maybe guideline.
Well, I just remember a rule about